Imagine holding a superpower, the ability to peer inside a living person, to see their bones, their organs, their brain, all without making a single cut. This isn't science fiction, it's the reality of modern medicine. Today on G Fun Facts Online, we're pulling back the curtain on the incredible story of medical imaging, a journey from a ghostly black and white photograph of a hand to AI-powered systems that can predict disease before it even starts. So let's dive in. Our story begins in a dark lab in Würzburg, Germany, on a Friday night, November 8, 1895. Physicist Wilhelm Conrad Röntgen is working late, experimenting with something called a Crookes-Hittorf tube, basically a glass tube with most of the air pumped out, used to study cathode rays. He's wrapped the tube in thick black cardboard to block out any visible light. But then he notices something odd. A few feet away, a small screen coated with a chemical, barium platinocyanide, is glowing with a faint, shimmering green light. He turns the tube off. The glow stops. He turns it on. It reappears. He knows the cathode rays themselves can't travel that far through the air. This is something entirely new, something that can pass straight through the black cardboard. He calls them X-rays, with X for unknown. For the next few weeks, he barely leaves his lab, eating and sleeping there, obsessed with understanding these mysterious rays. He discovers they pass through paper, wood, and even thin sheets of metal. But the most stunning moment comes when he places his own hand in the path of the rays. On the screen, he sees a ghostly image of his own bones. Realizing the historic nature of this, he calls his wife, Anna Bertha, to the lab. He asks her to place her hand on a photographic plate and exposes it to the rays for 15 minutes. The resulting image is one of the most famous in scientific history, a skeletal hand, her wedding ring clearly visible as a dark band. When Anna saw the image of her own bones, she reportedly exclaimed, "I have seen my death." The news exploded. Within weeks, Röntgen's paper was translated and reprinted worldwide. The public was fascinated and horrified. Newspapers ran wild stories. Department stores in London offered X-ray-proof underwear. But the medical community saw the true potential. By 1896, a hospital in Glasgow, Scotland, had set up the world's first radiology department. Doctors were using X-rays to find bullets in wounded soldiers and set broken bones with incredible precision. For this discovery that literally changed how we see ourselves, Röntgen was awarded the very first Nobel Prize in Physics in 1901, a fitting start to a century of medical revolution. X-rays were revolutionary for bones, but they weren't great at showing the body's soft parts, the organs, muscles, and blood vessels. The search for a new window into the body led scientists to an unlikely source, the ocean. During World War II, submarines were tracked using sonar, which stands for sound navigation and ranging. It works by sending out a ping of sound and listening for the echo. The time it takes for the echo to return reveals the distance to an object. After the war, researchers wondered if this same principle could be used on the human body. In the 1940s, a neurologist named Karl Dussek in Austria tried using high-frequency sound waves to map the brain, hoping to find tumors. But the real breakthrough came from a Scottish physician, Ian Donald. Working in Glasgow in the mid-1950s, Donald, an obstetrician, was frustrated with the limitations of X-rays for his pregnant patients. He had a hunch that ultrasound could be the key. His early experiments were rustic. He used a repurposed industrial flaw detector and practiced on slabs of raw steak with tumors embedded in them. His first major clinical success was distinguishing a benign ovarian cyst, which is filled with fluid, from a solid, potentially cancerous tumor. But his most famous application was yet to come. He perfected the technique for obstetrics, allowing doctors for the first time to see a developing fetus in the womb without using harmful radiation. This technology, now called sonography or ultrasound, is a cornerstone of prenatal care. It works by sending high-frequency sound waves into the body, from a handheld probe. These waves bounce off different tissues and organs at different rates, creating echoes. The machine's computer instantly translates these echoes into the black and white, real-time images we're all familiar with. It's safe, relatively cheap, and portable, making it indispensable for looking at the heart, abdominal organs like the liver and kidneys, and guiding needles during biopsies. It's all thanks to an idea borrowed from the high-stakes world of submarine warfare. The 1970s brought a leap so monumental it's hard to overstate. Imagine you have a loaf of bread, and you want to see what's inside without cutting it open. X-rays give you a shadow of the whole loaf. Ultrasound can see some textures. But what if you could see every single slice in perfect detail without ever touching the knife? That is the magic of computed tomography, or the CT scan. The idea came from two brilliant minds working independently: English electrical engineer Sir Godfrey Hounsfield and South African-born physicist Alan Cormack. Hounsfield worked for the company EMI, yes, the same EMI that signed the Beatles. In fact, it's often said that the profits from the Beatles' records helped fund the research that led to the CT scanner. Hounsfield's genius was to combine the power of X-rays with the processing power of a computer. Instead of taking one static picture, a CT scanner has an X-ray source that rotates around the patient's body, taking hundreds of images from different angles. A computer then acts like a super-powered mathematician, taking all these flat, 2D images and reconstructing them into detailed cross-sectional slices. The first clinical CT scan was performed on a patient in London in 1971. It took hours to acquire the image and days for the computer to process it, but the result was astounding: a clear picture of a tumor inside the patient's brain. For the first time, doctors could see soft tissues inside the skull with incredible clarity. Hounsfield and Cormack deservedly won the Nobel Prize in 1979. Modern CT scanners are unbelievably fast, capable of imaging the entire body in seconds. They create such detailed images that they can be stacked together to create 3D models of organs, bones, and blood vessels, allowing surgeons to plan complex operations with pinpoint accuracy. It's an indispensable tool for diagnosing everything from cancer and heart disease to internal injuries from a car crash. As incredible as CT was, it still relied on X-rays, which involves a small dose of ionizing radiation. The next great leap in imaging would do away with radiation entirely, using a fundamental property of our own bodies: water. Our bodies are about 60% water, and every water molecule contains hydrogen atoms. Each hydrogen atom's nucleus, which is just a single proton, acts like a tiny, spinning magnet. Normally, these tiny proton magnets are all spinning and pointing in random directions. But what if you could get them all to line up? This is the core principle of magnetic resonance imaging, or MRI. The foundations were laid back in the 1940s, but it wasn't until the 1970s that scientists like Paul Lauterbur and Peter Mansfield figured out how to use this principle, called nuclear magnetic resonance, to create images. The first human MRI body scan was performed in 1977. Here's how it works. In a nutshell, first, you slide into the long tube of the MRI machine, which contains an incredibly powerful magnet, thousands of times stronger than a fridge magnet. This powerful field forces all those tiny proton magnets in your body to align in the same direction, like trillions of tiny compass needles, all pointing north. Next, the machine sends a quick pulse of radio waves. This pulse knocks the protons out of alignment. When the radio pulse is turned off, the protons snap back into alignment, and as they do, they release a small energy signal. Different types of tissue, like muscle, fat, brain matter, and ligaments, release slightly different signals and take different amounts of time to realign. A powerful computer listens to these signals and uses them to construct an astonishingly detailed image. Because MRI is so good at differentiating between different types of soft tissue, it has become the gold standard for looking at the brain, spinal cord, joints, muscles, and ligaments. It's how doctors diagnose conditions like multiple sclerosis, find subtle ligament tears in an athlete's knee, and examine delicate brain structures without any radiation exposure. So far, we've talked about imaging technologies that show us anatomy, the structure of the body. X-rays show bones, CT shows slices of organs, and MRI shows detailed soft tissue. But what if you wanted to see how the body is functioning? What if you could see biological processes in action? That's where nuclear medicine comes in. This field sounds a bit scary, but it involves using tiny, safe amounts of radioactive materials called radiotracers. Think of a radiotracer as a tiny spy with a flashlight. It's designed to be attracted to specific cells or processes in the body. For example, you can have a tracer that's attached to a sugar molecule. You inject this into the patient, and it travels through the bloodstream. Now, which cells in the body are the hungriest for sugar? Cancer cells. They have a very high metabolic rate and gobble up sugar much faster than normal cells. So the sugar-based radiotracer accumulates in the cancerous areas. A special camera, called a gamma camera, can then detect the flashlight, the tiny amount of radiation being emitted by the tracer, and create an image showing exactly where the cancer is. The most prominent type of nuclear imaging is the PET scan, or positron emission tomography. A PET scan gives you a map of metabolic activity. It can show not just that a tumor is there, but how active it is. This is incredibly useful for seeing if cancer has spread or if chemotherapy is working. But a PET scan on its own is like a map of city lights at night. You see where the activity is, but you don't see the streets or buildings. That's why the real magic happens when you combine technologies. Modern scanners are often PET-CORT or PET-MRI machines. They perform both scans at the same time, then overlay the images. The CT or MRI provides the detailed anatomical map, the streets and buildings, while the PET scan provides the functional information, the lights. This fusion gives doctors a complete picture of both structure and function, leading to far more accurate diagnoses and treatment plans. For decades, medical images were captured on large sheets of photographic film. Radiologists would clip them onto light boxes, squinting to see subtle details. If a doctor across town needed to see the image, a courier had to physically transport it. The process was slow and cumbersome. Then came the digital revolution. Just like with photography, the shift from film to digital sensors was a game changer. Digital images could be acquired faster, with better quality and lower radiation doses. But the biggest advantage was storage and sharing. This led to the creation of PACS, picture archiving and communication systems. Think of it as a secure, hospital-wide version of Google Photos. A CT scan taken in the emergency room could be instantly viewed by a radiologist in their office and a surgeon in the operating room, all at the same time. This dramatically sped up care. Now, we are in the midst of another, even bigger revolution: artificial intelligence. AI, specifically machine learning and deep learning, is poised to transform radiology. Scientists are training AI algorithms on millions of medical images. These algorithms learn to recognize patterns associated with disease, patterns that are sometimes too subtle for the human eye to catch. For example, I could analyze a chest X-ray and flag a tiny nodule that might be an early-stage lung cancer, ensuring the radiologist gives it a second look. I can also automate tedious tasks, like measuring the precise size of a tumor on dozens of CT slices over time to see if it's growing or shrinking. This frees up the highly trained radiologist to focus on the most complex diagnostic challenges. The goal isn't to replace human doctors, but to create a powerful partnership, a human-AI team that can diagnose disease earlier, faster, and more accurately than ever before. So what does the future hold? The pace of innovation isn't slowing down. We're seeing the rise of techniques like 3D tomosynthesis, which is like a CT scan for breasts, creating a 3D image from multiple low-dose X-rays to find cancers hidden in dense tissue. We are pushing the boundaries of what we can see with molecular imaging developing new tracers that can light up specific proteins or genetic activity related to diseases like Alzheimer's or Parkinson's, long before symptoms appear. And the hardware is getting smaller and more accessible. Imagine portable, point-of-care ultrasound devices that connect to a smartphone, allowing a paramedic at an accident scene to check for internal bleeding, or a doctor in a rural village to perform a prenatal scan. The ultimate goal is to make imaging more precise, more predictive, and more personalized. From a shadowy black and white image of a hand that shocked the world, to 3D, color-coded maps of metabolic function analyzed by artificial intelligence, the evolution of medical imaging is one of the greatest success stories in science. It's a testament to our relentless curiosity and our desire to understand the incredible, complex machine that is the human body. It has given us the vision to diagnose, to treat, and to heal, and its future promises to be even more illuminating. Thanks for tuning in to G Fun Facts Online.